Hello, good evening, and welcome to week 2 of the live interactive session of Fundamentals of Micro and Nanofabrication. The course instructor is Professor Susovan Avasti and Professor Sankar Selvaraju from ISC Bangalore. I am the PMRF teaching assistant Vikas Pandit from IIT Jodhpur. This is a brief about me. I am a PhD scholar, Space Science and Technology at IIT Jodhpur. For more details, you can visit my webpage, which is given here, or all the recording of these sessions are also available on the YouTube channel mentioned here. In case you have some certain queries, you can even write to me over this email. Okay. So before delving into questions, first we will be discussing some basics. So as we know that this week 2, is about additive processing. This is the first part of the additive processing that covers defects and diffusion, and the second part is in week 3. So in continuation with the cleaning process we were talking about in the week 1, where we talked about the standard cleaning processes like piranha cleaning, RCA1 and RCA2. Now there are certain cleaning processes that need to be done even when we are doing subsequent processes. And sometimes you see that dust, dirt, solvent, organic or inorganic materials. So, in continuation with the cleaning process we were talking about, in addition to the piranha cleaning and the RCA1 and RCA2 cleaning, there are some other processes that are also used and are very frequent in micro and nanofabrication. The first one is ultrasonic cleaning. So, first one is ultrasonic cleaning. In this case, we are using ultrasonic waves, which are waves in the, like we already know that the frequency that we are able to hear is 20 hertz to 20 kilohertz, right? So frequencies beyond this range are used to clean it. Since they are having higher frequency means they will have higher energy of dislocation. So these are basically sound waves that create pressure waves in the liquid. It is typically water, acetone, IPA kind of thing. So it will make the molecules of this liquid vibrate as per uh, as per the frequency that we are applying. Then it creates cavity. Okay, collapse, uh, collapse of bubbles causing energy release. So, in a sense, it will agitate the particles and it will create bubbles around it and make it go away from the surface. This actually, uh, this is in addition to chemical cleaning, like it is helping the chemical cleaning. It is not something being used altogether. So, in some solvent like acetone or IPA, when your wafer is kept, then these ultrasonic waves are used to to help it to increase the efficiency of our cleaning. Okay, and this is very effective in removing insoluble particles. Like suppose we have kept the wafer in acetone, and there is a particle that is not soluble in acetone, but when we are putting it in, uh, when we are using ultrasonic waves, such particles will also move, like go into the solvent due to this agitation of the particle. but there are certainly some disadvantages associated with it, that it can damage small feature. If we have very small feature or small uh, structures that we have already made, that may be damaged due to the high frequencies, as it is able to like put some energy over it, it can vibrate and break, or it can remove. So there is a trade-off between cleaning efficacy and feature integrity. So they are generally they are above 20 kilohertz, right? So 20 to 100 kilohertz are used. This is the ultrasonic frequency that is used in the case of uh, ultrasonic cleaning. Then there is something called as megasonic cleaning. It is the same thing but at a higher frequency. So this range is 700 kilohertz to 1 megahertz. This is more effective for small particles, which is in case of ultrasonic, it is not. But this will damage the features even more. So we have to be very critical, and we have to be very careful in using this. Then is the solvent cleaning, and this is one of the most common way cleaning is done, while like almost after every step. Okay, here organic solvents like acetone and IPA are used to dissolve organic contamination. Most of the contamination that occurs after this cleaning process, RCA1, RCA2 has been done, HF dip has been done. After that, sorry, after that, we are doing some subsequent processes. In this subsequent processor, some organic contamination may come. Like sometimes we are going for lithography, this photoresist comes and these things. So to remove this, we are using organic solvent like acetone and isopropyl alcohol. These are mostly suitable for metal coated wafers. Since metal we cannot put in the piranha cleaning, or we cannot put for piranha, or even this what you say RCA1, RCA2, HF dip will also damage it, right? So for metal coated wafers, we are generally going for solvent cleaning. Very the common solvents are acetone, methanol, and IPA. It is something like sequential wash, washing in uh, acetone, then taking it out, rinsing in DI, drying it with dry nitrogen, and then again rinsing it in methanol. Then again taking it out, uh, rinsing with DI, drying it, then uh, again IPA dip. Like it is sequential, and with it in each step there will be a DI dip, DI dip or DI rinse, and then drying with dry nitrogen. And why is it so that we are going in this sequence, like we are not doing it in any other sequence? It is that we are like we are removing the stains by like we are removing the stains by moving from most to least volatile solvent. If we go by IPA, methanol, and then acetone, the effect will be like some stains can be there. Like acetone itself can create some stains. Okay, so in order that the cleaning happens as well as no stain is left. So acetone, this is volat most volatile amongst acetone, methanol, and IPA. So we are first going to acetone, that will leave some stains, that will be removed by methanol, and that will do further cleaning, and then IPA will remove the stains of methanol also. Okay, and then the step, in fact, mostly in after each step, actually, blowing dry is used to avoid residue formation. And some people like go from acetone to methanol and IPA with DI washes. But hello, yeah, Somnath, am I audible?
Yeah,
Yeah, okay. So with each subsequent steps, some people do this blow drying, or some people either prefer by doing the sequential wash and then go at the last they will do the blow dry. Okay, but in case of gallium arsenide cleaning, it is like one more material, that is TC or trichloroethylene is used, followed by acetone and methanol. Okay, then there are some other advanced cleaning techniques in which the objective is to reduce the steps that is used, as well as uh, to reduce the chemical and environmental impact. Okay, the methods are like ozone and megasonic showers. We have seen ultrasonic and megasonic, right? So megasonic showers as well as ozone are used. One example is OmiClean, where ozone in water is used. Water will be DI water. Okay, this oxidizes organics and metals. Then this is followed by HF dip that removes the chemical oxide that is found due to the presence of ozone. Ozone is oxygen, so an oxide will be formed. And then ozone megasonic shower that removes the remaining contamination. Finally, HF dip and DI water rinse is done. This to ensure cleanliness. The thing, the advantage here is that the chemical uses are reduced. We are not dipping the whole wafer inside the chemical. Instead of that, we are using shower and baths. Like unlike dipping it and keeping it for some time, we are just using bath that will require less chemical, and we are using some environment friendly chemicals. So that also makes it a bit environment friendly, and cost effectiveness also increases. Okay. Then comes another technique, that is dry surface cleaning. Whatever we were talking till here, it was about wet cleaning methods. They were using chemicals. Okay. Some dry surface cleaning uh, methods are UV ozone, thermal cleaning, particle showers, that is plasma cleaning. The advantage associated with these are there are no liquid waste, and it is particle free cleaning, and it also reduces handling of hazardous chemicals, so we are also less exposed to such chemicals. So here you see there are two images that I have shown. The top one is of UV ozone cleaning. In this case, UV light is used, as well as ozone gas, O3. Ozone gas is used for the cleaning purpose. Whereas in the second case, where we are using the plasma cleaning method, okay, here oxygen plasma, O2 plasma is created, and this is used to clean the surface of our wafer. Then once we have done this cleaning, now the next step is that we need to know whether our wafer is ready for for the subsequent step or not. So there are some detection methods that are used to detect the particles as well as the chemicals that are present on the surface of they have been removed or not. The most basic one is the optical microscopy. Using optical microscope, We see whether some particles are there or not. Then comes SEM, that is scanning electron microscopy, TEM, tunneling electron microscopy, AFM, atomic force microscopy. We'll be covering this more when we go to, I think, 7th or 8th week, where we will be talking in details about characterization methods and all. For chemical, things like XPS, SEMS, EDEX, CV measurements are used. These are methods used to determine what chemical composition is present on the top. So ideally, if you are taking a silicon wafer, nothing else except silicon should be there. And even if it is there, it should be in very minute scale. Like it should not be visible at, like it should not have any traces visible kind of thing. Okay. Some examples are dark field microscopy. This is used to highlight particles. Like when you use the dark field microscopy, if there is a particle, that will appear as bright spot, and if there is no particle, it will just be a complete dark image. Okay. Then is SEM imaging. This identifies particles before and after cleaning. Okay. And then there is something called as electroluminescence. This detects defects via electronic property variations. Different defects have different electronic properties, right? So now let's come to defects. What kind of defects can be there in the semiconductor? Okay, we have talked about particles and all, but the semiconductor that we are getting, or the uh, silicon or gallium arsenide, whatever we are getting, that also can have some defects. These defects are both uh, of our disadvantage as well as of our advantage. We'll see them in this lecture. Okay, so defects can be categorized as four types. 0D defects, that is point defects like vacancies and interstitials. So you can say something at the atomic levels. Okay, these are zero dimensional defects. Then comes 1D defect, that is one dimensional defect. In this case, they are dislocation and disclination. That means you can say a straight line or a line kind of defect is 1D defect. As we know that line is something that don't have a width and uh, height but have a length. Okay, so similar to that 1D defect where something that is creating a line kind of pattern, that is creating a line kind of irregularity. Then comes 2D defect, that is grain boundary and surface. That means a surface kind of, like the whole crystal is, suppose that it is having some irregularity at a specific plane, that will be grain boundary surface and surfaces. These are two-dimensional defects. Then three-dimensional defects are precipitates, voids, and cracks. That means that can be a volumetric defect, you can say, where the defect will not just be in sense of single atom or a line of atoms or plane of atoms, but more than that, like beyond that, in the sense it can be creating defects in all three directions. Why is it important? Because these defects impact the device performance. The device that we are going to make finally will have effect of these defects in the semiconductor. So ideally we try to start with defect-free semiconductor, but these defects might arise during our processing also. We need to know both the things, how to create defects and how to remove defects. Sometimes we purposefully also create some defects. Okay, so let's first discuss about 0D defects. Okay, these defects are, as I said, in one dimension, where one or more than one atoms at discrete positions can be involved. Okay, the first type of this is vacancies, where you see if these are all silicon atoms. Okay, so ideally there should have been one silicon atom here also, but it is missing, and this missing atom creates a vacancy, and this defect is called as vacancy defect. Okay, if we see the lattice, one atom is missing. Okay, then there can be a chance that an extra atom of silicon or maybe some other, like let's say boron, has come here. Okay, you see, what it is doing is that it is sitting in between some place where all the silicons were present, but an extra atom has arrived there, and it is in the interstitial place. That means not at the crystal positions, not at the crystal points, but at the not at the lattice point, but at the interstitial. There can be two type of this interstitial interstitial defects. One can be self-interstitial, in which if an extra atom of silicon itself, or if we are talking about germanium or gallium arsenide, the same material is present. The other one can be of the impurity, like I talked about, boron is present here, right? Then comes the third type of point defect or zero dimension defect, that is substitutional impurity. In this case, one atom is missing and is replaced by some other atom. This is mostly about, if it is replaced by the same material, then certainly it will not be a defect. So it is mostly when some impurity is there, like in this case, if it is silicon, 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 silicon. Here also a silicon was supposed to be there, and let's say boron is there. Okay. In this case, it will be a substitutional impurity. So if you see all these figures, you will notice one thing. That is, whenever these defects are happening, there is some irregularity uh, coming out of the, like the lattice is not a perfect lattice now. When there is something missing, you see this pattern. It should have been straight, but actually it has got a dip here. So, and in this case, this thing has this right side curvature has been there. In this case also, the silicon atoms are getting closer. They should have been at a different position. Okay, so there can be two type of stress developing due to these point defects. One is compressive stress, that is when a larger atom is present. The second is tensile stress, if a smaller atom is present. Like in this case, it will be a tensile stress. Okay, and in this case, since it is sitting at a like at a position that it was not desired, like all the things are filled and something has been forcefully inserted, it will be a compressive. This will be compressive, and this will be tensile in nature. Okay, so stresses develop due to this point defect. Then comes line defect. Here, in this case, there are edge dislocations or screw dislocations. Like there are two type of dislocations in case of line defect: edge dislocation or screw dislocation. In case of edge dislocation, an extra half plane of atoms, like you see here, this is not going completely, but it is just an half or incomplete plane of atoms is present, and this is leading to something called as edge dislocation. Whereas if we have spiral stacking of crystal planes, like if you see here, this is this plane was perfect, this was perfect, but here, somewhere here, some imperfection has arose. Okay, and this is called a slip plane, and here a screw dislocation or spiral stacking of crystal planes has occurred. Okay, for example, you can see for strontium titanate, this is an image taken from this paper. This is an HRTM image showing an edge dislocation. So you see these lines look parallel, but when we see this part, it is not parallel to these lines because some edge dislocation is happening here that is creating the pattern, that is some extra raw has got inserted here. Let me change the color. Some extra raw of atoms has got inserted, uh, molecules have got inserted here in the crystal plane, leading to this edge dislocation. Okay, then comes the next, that is surface and grain boundary defects. Okay, surface defects, that is the interface between different materials or phases. That is example is like crystalline silicon we are talking about is perfectly crystalline and this thing, and then we have an amorphous silicon nitride deposited over it. So the interface, like this interface will actually develop some boundary defects because it is not going to be perfectly matching to the uh, crystal below. Okay, then so this will occur throughout the surface. Okay, then comes grain boundary defect. Like we have a perfectly crystalline material here, this one also, this one, but when they are joining at one place, this part and this part, like the two parts are not matching. Like if this is one, two, three, there are three crystals, like crystalline structure, they are not matching crystal to crystal. Then there is some defect throughout this merger or place where these boundaries occur. Okay, so there can be two type of grain boundaries: high angle or low angle grain boundaries. What is the effect of this? This is that it increases the defect density because it is not just one but multiple defects. Okay, as well as this will lead to some change in mechanical and electronic properties, like the flow of electrons that was expected to be, say, at some mobility or some speed with some resistance, that will vary because there are some uh, unwanted boundaries that it will have to overcome. Okay, so this will play some role. Then we have talked about the problems and we have seen what are the defects as well as we have talked about the problems. But sometimes we purposefully want these defects. And why do we want this? Because if you see, you must be aware from your intermediates also, yet we will discuss that if we have intrinsic silicon, pure silicon, all silicon, let's say silicon have four valence electrons, right? Silicon is joined. So in this case, there is no extra binding site available for the movement of electrons in its perfectly uh, its perfect state. Okay, all of it is actually connected to silicon. But if we introduce some defects to it, like if we put boron or phosphorus, let's start with phosphorus. Like you see in this case, phosphorus have 5 valence electrons. So it is bonding here, 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 but one extra electron is now available for the conductivity in this. Okay, this is desirable to increase the conductivity, and that also electronic conductivity is there, is increasing, and that is why it is n type or negative type, since electron is present in excess. Whereas if we are doping, if we are adding boron and it is sitting at an interstitial site, or it is like replacing the silicon atom at a position, what will happen is that in case of boron, we have only 3 valence electrons. And these 3 valence electrons will actually create bonding with the 3 silicon, but one part where silicon wants to bond will remain empty, and here a hole is created or a vacancy is created. And that's why it is called as p-type, since it has less number of electrons than required. So it is ideally positive in, like we say, we represent it by positive. Okay, this is important to change the conductivity of the material that we are making for the tuning the conductivity of the semiconductor. And the other thing is that you must have seen and heard about PN junction, diodes, transistors. All these are made using this difference in this doping level, P type and N type, and such junctions are created. And they play a major role in electronic industry. And that is why to create this, we need to purposefully create some defects or do doping or adding impurities. And this is done using a sim the simplest way to do this is using diffusion. Okay, what is the mechanism of this diffusion? It can be done in two ways. One is interstitial diffusion, or the other one is the substitutional diffusion. In case of interstitial diffusion, impurity atoms move through interstitial sites. So impurities are added and then they move to. I think there is some lag. Just a minute. So let's continue again. So there can be two mechanisms of diffusion. One is interstitial diffusion, that is impurity atoms, that is, let's suppose this one is moving through interstitial site, that is in not at the lattice positions, but in between the lattice positions, somewhere between the atoms. Okay, this is a faster process, requires less activation energy, typically in the range of 0.5 to 1.5 electron volt. Very common for small impurity, that when we are talking about small or larger, that means in compared to the lattice atoms we have. Okay, say hydrogen or oxygen, which are smaller in size compared to silicon. Okay, whereas there is another way of diffusion, that is substitutional diffusion. In this case, the impurity atoms move through vacancies. So one, in a sense, one atom from the lattice moves out or is knocked out, and then it is filled by an impurity. It is a slower process, needs higher energy since it has to knock out the previous atom, right? So it is typically in the range of 3 electron volt, and it is common for larger impurities like arsenic and antimony. Okay, so how do we model or how do we estimate the diffusion? It is done using the Fick's laws. There are two Fick's laws. One is flux is proportional to concentration gradient. That is the uh, amount of the impurities present, the concentration of impurities will determine the flux, or the you can say the flow of these impurities. So it is given by J equals to minus D. This is the constant that we are getting here, dc upon dx. Here a negative sign is there, minus D, right? This indicates that the movement is from high to low concentration. So when we are doing the diffusion will always take place from the higher concentration side to the lower concentration side. Then the thing is, the second law is that this concentration changes over time, and this is given by dc upon dt equals to d of d square c upon dx square. So x is the uh, position. Okay, so at a given position, the concentration will change with time. Okay, so this fixed law is used to model and estimate the infinite dopant source, that is constant, to create the constant surface concentration. So we are changing the concentration of the dopant so that we get a constant surface concentration for our doping to occur. Then second option can be to create finite dopant source, to create Gaussian profile. Gaussian profile, we know, is say, like the concentration will rise and then the bell-shaped curve. Mostly it is presented by, this is x and we can say this is concentration. Okay, so a Gaussian kind of profile is to be created. In that case also this is used. Okay, so what are the practical considerations for this diffusion? Okay, one is the diffusion coefficient D. Okay, it is having an exponential dependence on temperature. So temperature will also play a role. In fact, the diffusion process takes place at higher temperature, not at room temperature. Higher temperature increases D significantly, and once that is why it is taking at higher temperature. That means the diffuse, since we have uh, the constant D there, and if you see, the flux will increase if we have higher D, and D is directly proportional to is having a dependence to temperature, and that also not direct but exponential. That means with the small increase we of temperature, we will see a very large increase in the significant increase in T. Okay, then comes impurity and diffusibility. All impurities or all doping materials we use don't have the same diffusibility. Like interstitial impurities like gold and copper diffuse fast, whereas substitutional impurities like boron and phosphorus, which are being used for doping, diffuse slower. Okay, then comes different kind of sources that we can use. Like we can either go for diffusion, we can go for some solid sources like boron nitride or arsenic oxide, or liquid sources like PoCl3 or boron halides. Okay, or there can even be gaseous sources according to our need, like diboron and phosphine. So the greatest takeaway from all the talk about diffusion is that control the temperature and time to manage the diffusion depth and concentration. We have two things. We don't we may or may not be wanting the whole thing to be diffused. Okay, we might want this diffusion to occur till some place, some depth, as well as we might want to control how much diffusion should occur, how much doping should occur. And these two can be controlled by controlling the temperature and time. Okay. Then now this is the theory. Now let's see how it is actually done. Okay. The objective is generally to create controlled doping in selected region. Okay. Because we have seen that when we were starting with the ingot itself, we were doping it. So ideally, you can say that we already have something like P-type silicon, or let's say we have a N-type silicon. Okay. So now we don't want to convert it to P-type or something like that, but we want some selective regions to be, say, P-type. Okay. So we have to do control doping, and that also in selected regions. So the technique is using diffusion mask. So we have the wafer, we are masking some areas and we are opening some areas. Let's say we are covering this area with oxide or nitride, silicon oxide or silicon nitride. So these patterns are created at first that will cover the area, then this diffusion will be done. And ideally, what should happen is a structure like this should be made, okay? That the area below the mask will have no diffusion and the open area will have diffusion to certain depth. But actually, it occurs something like this, where the diffusion occurs even somewhat below the oxide, and actually it will not be square kind of, can say something like this. Again, a Gaussian kind of profile will be formed. Okay, so you can actually create some alteration in the mask itself to reduce the this outgrow, right? So the purpose of this diffusion mask is to prevent diffusion in the mask areas. So we want only the diffusion in some selected area. The second thing is that it cannot be anything, like the mask cannot be anything. It have to be non-contaminating. That means it is not disturbing the whole process. Okay. And it must be removable. It is not that it remains permanently there, because we are just using it for some small purpose which we want to remove later. And it should be of appropriate thickness. It should not be very thick or very thin. Like it should be of adequate thickness, and that should be able to withstand all this process of doping or diffusion. Okay, diffusion is mostly done in two step. Sorry, it is not just done in one go. It is done in two-step process. Okay, why two-step? To achieve better control and repeatability in doping. It is not that today we are doing this at one parameter, and next day it is being done at some other parameter. Like with the same parameter, it will not give the same result. It should not happen, right? So we are doing it in a better controlled way. Okay, so two steps are there. First one is pre-deposition. Second one is drive-in. Pre-deposition is a low temperature process where we are depositing the dopant that we want on the surface. Okay, so you see that this is a mask that we have used, SiO2. We are putting, like we are making the dopant arrive at the surface, top surface. This is a low temperature process. Okay, in a sense, we are creating the concentration here. We are creating a higher concentration of the dopant here. Okay, like POCl3 forming phosphosilicate glass on the top. Then comes the drive-in, that is a high temperature process. This diffuses the dopant deeper into the silicon. So from the top, it will go in. Okay, and on the top, since it is a high temperature process, so silicon will also oxidize on the top, and this formation of silicon dioxide layer will actually prevent like going this for this diffusion to go very deep. It will actually control the amount of diffusion also. Okay, for example, a pre-deposition can occur at something around 800 to 900 degrees Celsius for 10 minutes in oxygen, and then this driving can occur at 900 to 1000 degree in oxygen for 10 to 30 minutes. So you see the pre-deposition step is uh, at a lower temperature as well as for lower time period where the we are creating the concentration gradient. Then drive-in is where we are making it go till the required depth, and on the top SiO2 that forms that will actually act as a diffusion mask, or you can say that will diffusion stop, create a diffusion stop layer where it will prevent the further uh, further concentration of the dopant gases to be coming there. Okay, then there is something that is interstitiality and enhanced diffusion. Okay, this is interstitiality diffusion is combination of interstitial and substitutional mechanism. So we have seen that there are two types of mechanism, interstitial and substitutional. So it is combination of both, and it has the advantage that the it is having a faster diffusion due to the involvement of silicon interstitials. Okay, what is the enhanced effect of this enhanced diffusion? Due to the oxidation or nitridation, it creates interstitial or vacancies, and this enhances diffusion. So the mask, when we are creating the mask itself, there are some interstitial or some vacancies are created, and when we are doing the diffusion, these vacancies will enhance the diffusion process. Another way is using the field enhanced diffusion. So we are using some electric field for this space, like the dopants to be charged. Okay, and since it has charge, it will easily like its diffusion will be enhanced due to the presence of this electric field charges, and it is done in case of boron diffusion. Due to the presence of electric field is enhanced, and that makes it faster. Then once we have done this mm, diffusion or doping, we again just like we check the cleanliness, or we check that there are no particles and the materials, no extra metals present on the surface. After doping also, we want to check whether we have been successful or not, and whether the desired resistivity or desired conductivity is achieved or not. Okay, so there are two methods generally used. One is four probe method, 4-point probe method, that uses the resistivity to infer dopant concentration. It is a simple four probes, four electrodes at some specific distance, say S. Okay, all of them will be having the same distance. The two inner electrodes are connected to a voltmeter, and two outer electrodes are connected to current source. Okay, and if it is if a voltage V is applied between the inner two electrodes, okay, current through the there will be some current through the outer probes, and that is I. Okay, and all these needles or probes are spaced at distance S. Okay, then the seat resistance in ohm per square centimeter or meter, whatever be the unit of S is given by V upon I pi of log 2. Because if you see the distance, it can like you can see that the current somewhat flows like this. So this S will cancel out, okay, if it is all equal. Okay, the needle spacing, if it is equal, it will cancel out. Okay, and then this value pi upon log 2 gives us 4.5324. Okay, and using this method we are able to check the the seat resistance and thus infer how much doping has been done, because if we measure before and after doping we will be able to understand the difference. Okay, then there is some one another method, that is secondary ion mass spectroscopy. In this case the surface is sputtered, okay, and like some materials are sputtered or deposited over it, and the mass of these dopant profiles are analyzed. This gives us the concentration versus depth profile. This is more precise, but it involves more complex mechanism. Okay, then there is another method that can be used to create introduce dopants. Okay, and that is ion implantation. This is more precise compared to diffusion, since we have proper control over the dopant ions and the depth of the ions. Okay, this is uh, done by shooting ions at high speed into the substrate. This uses ion source specific to the dopant, that is phosphorus, boron, etc. Okay, here this setup, though it looks small here, it is very big. Like you can say a very big hall is required for this setup. Uh, and this ion source, this whole ion beam is collimated and then controlled, and a raster kind of structure can be raster kind of profiling can be done, where X and Y plates are fixed and then controlled amount how much has to be put in. Okay, and this whole thing has to be done in vacuum. So ions travel a long area, they are collimated, they are filtered out, like all unwanted ions will get out and only the desired one. So that profile is well known, that under the influence of this magnetic field, since like suppose we are going for phosphorus, so how much deflection the phosphorus will make. If we are going for boron, how much deflection the boron uh, ions will make, that is already known. And in vacuum it is even more precise, like we don't have to worry about this Brownian motion and all. Okay, this is having more precise control of doping compared to diffusion. In case of diffusion, we were relying on the concentration, and it might be that the temperature, although was given, but the temperature are not uniformly reaching all the places, and there can be other factors like the concentration might be getting obstructed due to some some shadowing of the mask and all. But in this case, no mask is required ideally. Okay, we know by point where we have to put the ions. Okay, this is more precise. And how the process occurs is that the ions that we have, say phosphorus, okay, they are directed precisely, like this is the wafer and we want to create a doping profile, say like this. So it will be directed towards here, like it will not be directed anywhere else. It will just be directed at the places that it is wanted. Okay, so there will be ions will be bombarded, but not as a whole at specific points wherever we want. Okay, so it works with collision and penetration into the substrate and thus creating the dope layer. But here there is a problem that this, since it is bombarding something on the surface, it will create more damages to the surface. And that is why an annealing is used, like after the process is done, annealing is done to repair damage and activate dopants. Since they are just being planted, okay? So once you do annealing, they will adjust themselves in the crystal as well as the top imperfections like the damages that will that will get uh, relaxed and adjusted. Okay, it can it will lead to Gaussian distribution of implanted ions very perfectly since we have more control. There are two important parameters, that is projected range and strike zone, that will determine the doping. Okay, then what are the challenges associated with this whole process? The first one is channeling, that is ions travel deeper along crystallographic planes, but we want them to be controlled. We don't want them to be going very deep somewhere. If by chance they are going into the crystallographic plane, they will go very deep. Okay, then the second one is damage accumulation. As we talked about, there is some damage on the surface. Then the metallic impurities from the chamber, since such high vacuum chamber and this magnetic field, they require some metallic parts, and these metallic parts will certainly lead to some impurities in the process. Okay, so these can actually sorry, this can actually lead to some contamination in the process. So what are the solution for this channeling? We are doing the tilted implantation. So it is not being done directly face to face. Some tilting of the wafer is done and then the implantation is done so that it does not go in the crystallographic plane, and so we don't somewhere we don't get very deeper uh, profiles. Okay. The second is since since channeling is there as well as contamination is there, so a very thin oxide layer on the top is used that diffuses the ion flux, as well as contamination will also not go deep. It will remain on the oxide, and that oxide can easily be removed in the further processing. So this is what we have talked about in the this week. The next thing is we will be solving some problems related to this week. Okay, so let's start with our problem one. This is, at what frequency is ultrasonication performed? It is 2200 kilohertz, 2200 megahertz, 2200 millihertz, or 2200 microhertz. So remember, we talked about it is when we talk about ultrasonic, it is beyond the human audible frequency range. Okay, and audible frequency range is 20 hertz to 20,000 hertz or 20 kilohertz, right? So it should be above this. So if we see, A is a range above this, B is also a range above this, C and D are directly above. But if we see properly, this will be too high and it will actually break most of the features that we have, and that is why we are mostly using 20 to 100 kilohertz. This is the uh, this is for ultrasonication. For megasonication, we have slightly higher frequency range. Okay. Now, let's come to question 2. That is, identify the correct sequence of solvent cleaning. Acetone, IPA, TCE, methanol. IPA, TCE, methanol, acetone, TCE, methanol, acetone, IPA, or TCE, ethanol, methanol, IPA. So remember, we talked about one thing, that is solvent cleaning always goes like from volatile to less volatile. Okay, so in the sequence, the volatility should decrease. So TCE is more volatile than acetone. Okay, so if we see TCE should be before acetone, so this is fine. Then methanol is less, methanol and IPA both are less volatile than acetone. So these two, but in between methanol and IPA, IPA is less volatile. So the answer will be D. That is TC followed by acetone, followed by methanol, followed by IPA. Now let's come to problem 3. Which of the following is the method to detect particulate contamination in a sample? UPS, XPS, SIMS, lifetime measurement, PLN, EL measurement. So we have seen in the lecture that PL and EL measurements are used for detecting the particulate contaminants in a sample. Okay. Okay. Now let's come to problem 4. That is, which of the following is a 0D defect or a point defect? Dislocation, grain boundary, twins, or Schottky defect? So as we know that in case of Schottky defect, one uh, one single atom uh, can be moved from one place to another, and that is why this comes as this comes under 0D defect or point defect. Okay. Now let's come to problem 5. Given the diffusibility of element at 900 degrees Celsius in silicon is, for gold, the diffusibility is 2 into 10 to the power minus 7 centimeter per second. For copper, it is 3 into 10 to the power minus 6. For phosphorus, it is 10 to the power minus 14. And for iron, it is 9 into 10 to the power 17. Which element will diffuse slower? So all these are at different, like all of these are at same temperature. So these are values of D for specific material. For gold, it is given as 2 into 10 to the power minus 7. For copper, it is 3 into 10 to the power minus 6. So phosphorus 10 to the power minus 14, and iron it is 9 into 10 to the power minus 16. So that, so which will diffuse slower? In this case, whichever will be having the lowest diffusibility will actually, like lowest value of D will actually be having the lowest like lowest diffuse not diffuse, this D itself is diffuse, it will diffuse the slowest. Okay, so if we compare in this, all of this, they are in 10 to the power minus 7, minus 6. So we have the largest for copper, 3 into 10 to the power minus 6, followed by 9 into 10 to the power minus 7, that is iron, then gold, then phosphorus. This is 10 to the power minus 17, which is the smallest, like in the decreasing order. Okay, so phosphorus should be the one which will diffuse the slowest. In ion implantation, lighter ions, we are talking about problem 6. Okay, in ion implantation, lighter ions will have high penetration and high struggle, low penetration and high struggle, or high penetration and low struggle, or low penetration and low struggle. So since it is lighter, yeah, since it is a lighter ion, it will be able to go to uh, like go deep into the material, and so it will have higher penetration and higher struggle. Okay, next question is, so this was about the mass. Okay, lighter ion. Next is, in ion implantation, high energy ions. So we are not talking about mass now, we are talking about energy. So if we have two ions, one is having higher energy, the other one is having lower energy. The higher energy ion will have high penetration and high struggle, low penetration and high struggle, high penetration and low struggle, and low penetration and low struggle. Again, when something is being bombarded with a higher energy, it will be able to penetrate deeper, okay, and will have higher struggle. So for a high energy ion also, it will have high penetration and high struggle. So for high penetration and high struggle, we should have low mass, high energy ions. Next is, in again in context of uh, so in context of ion implantation, the the channeling effect, the channeling will have effect on the weight of the ion, concentration of the ion, penetration depth, or the struggle. So it will have, since weight of the ion is predetermined, that is not based on this, as well as the concentration of ion will depend on the concentration we want we bombard. Okay, but it will have the effect on penetration depth and struggle. And how is this overcome? This is overcome using two methods. One is using by slanting the wafer, and the second one is using a oxide layer, a thin oxide layer. Okay. Channeling depends on dose, crystal orientation, weight of the ion, or concentration of the ion. So as we have discussed in the previous question itself, the channeling will depend on all of these. Okay, dose as well as crystal orientation, that is the primary thing that determines the channeling. The dose will also determine. Weight of the ion will have effect on channeling, and the concentration of the ion. Then problem 10. To reduce channeling, we do which of the following? Using screen oxide, increase the concentration of the ions, tilt the wafer, or reduce the weight of the ions. So first one is already correct. We know that we are using screen oxide. Second one is increasing the concentration of the ion and tilt the wafer. So A and C are correct. and we can also increase the concentration of the ion to just just a minute, let me okay. So to reduce channeling, we use screen oxide, we tilt the wafer as well as we increase the concentration of the ion. Increasing the concentration of the ion will reduce the channeling. So that's all. In the next week, we will be talking about additive processing. Like this was also part of the additive processing, and then is additive processing with native films. Okay. You can ask any questions or you can write to my email, which I have provided in the beginning of the class. So thank you. See you in the next class. That's all for today. Thank you. Have a nice day.